Today I have something very special to show you. It's the beginning of 2025 and we are releasing our new Summit G4 series trumpets tomorrow. And what I'd like to do today is give you an in-depth overview of how they were designed, how they were made, and of course why they are so much better than the third generation series Summit trumpet. So I'm going to dive right in and talk all about this horn. And actually I have two of these, two variations, and there will be others that come out as well. So let me first show you the Honeycomb variation, which is a step up from the standard. This instrument was designed to be lighter and more efficient than the standard Summit, which we will demonstrate in several videos. Now let me show you the standard model, which is known as the simple strut. We just put strut on the name of that one. And you can see the top bracing has these little struts in it. I'm going to talk all about both of these horns in detail so you have a really good idea of how and why they're different, how they were engineered differently, and really what makes them better and why you'd want to own one. Tomorrow will mark the 29th year that I've been building trumpets, and we're over 33 years into research and development because I started really studying and building accessories about 4 years before that. And this Summit series has been really the top of the Harrelson line in terms of playability, efficiency, and of course versatility. And our goal has always been to make these as easy to hold and perform with as possible. Now, one of the complaints many years ago was that they were too heavy. The third generation became much lighter, and now the fourth generation is considerably lighter than the third, and you'll see more improvements as we go. The G5 will focus on even lighter materials. That does bring the cost up, but it brings the weight down. So you will see the G5 series later in 2025, which will feature stainless steel and titanium and aluminum. But for now, we're looking at the G4 and the materials that we're experimenting with all through 2024 and that we're going to introduce into the fourth generation will be brass, which is lead-free, bronze, which is lead-free, and copper. And the first two materials we have right now are brass and bronze. Copper will be coming. I will show you, I've got a whole huge table here laid out with all the components and all the different pieces that we have tested over the last year to 2 years, and we'll discuss all those materials. For those of you who follow my work regularly, you know that I've been working on metal 3D printing for a few years now. And before that, I was working on quite a bit of other materials for 3D printing. And I was the first one to say maybe 10, 15 years ago that 3D printing will never get to the point in my lifetime where it will be suitable as a material for trumpets. Well, I'm the first one to say I have to take that back. I was wrong. I have spent a lot of time working with industry leaders and the companies that develop all of these technologies, and with their expertise and their help and their guidance, and of course a lot of improvements in the process on their end as well, I'm 100% confident in saying that we can 3D print most, maybe even all of the components for a trumpet. I know that because I've already been doing it, and some of you have seen the things that we've done in the past, but we have explored a lot of different materials, including nylon, multiple resins, and in the FDM process, you know, everything from cornstarch to recycled wood to different kinds of carbon fiber. We've also experimented with, on the metal side of things, aluminum, brass, copper, stainless steel, other types of steel, titanium. Those are the big ones that we've really worked with. And we have 100% proven that the trumpet can be made from these other materials. And some of these materials are better than others, but they all have the potential to bring down the weight in terms of how heavy the horn is, and also increase efficiency by a lot. Now, one of the big secrets in doing this really is having the software and the understanding of how to design a product or a component to be able to take advantage of metal and other types of 3D printing. And that really is probably on the designer side, the hardest part. And for me, I've been working with the highest end software developers to understand how we can do this. And we've invested, probably $100,000 in software over the years to just be able to do everything we do with trumpets. In 2024, really the end of 2023 through 2024, I know we've invested probably about somewhere between $150,000 and $200,000 into researching and developing the G4 and G5 series trumpets. And that may not sound like a lot to some of you who are in other industries, but for trumpet players that might sound like a lot. It's not a lot in terms of research and development. It's very small if you were to compare it to a lot of other companies, but for our company it is a significant investment, and it's been a significant investment in my time. Keep in mind, I am the developer. I'm the only engineer at Harrelson Trumpets. I have always only been the only one, and what that really means is that we're limited to what I can come up with and what I can learn and my skill level. So that has always been a challenge, educating myself and getting better at this. But what I want to show you today are some things that I think have the potential to steer the industry in a completely different direction than it's ever gone. And some of these things might blow your mind. And for sure, I am 100% sure of this. They're going to change your playing for life. And I know that because I have developed all different types of technologies to build trumpets. And what I have learned is that as long as we have checks and balances and feedback from our customers, we're always improving that process. And there are a lot of things that I have created over the years that led to, maybe not dead ends, but they led to an area that became either too expensive or too difficult or too costly. And I've been steering through all the different processes over these years, really 33 years, to find what works for you guys. And the balance has to be cost to efficiency and versatility, and also the weight of the instrument. That's a factor because the simplest way to improve efficiency is to add mass in certain places, and you don't want the trumpet to weigh 5 pounds or 10 pounds or something like that. So with all that said, I'm going to start showing you some of these components and talk a little bit about them, and this is going to help you understand how and why the G4 series is so completely different. And remember, G4 just simply stands for the 4th generation of the Summit series. So first thing I want to show you is this spinning top, which is not even complete. There's actually another component that goes to this that would slide on here, and I didn't grab a complete one simply because I want to show you the parts that were 3D printed and machined. So let's spin that again. And depending on how good I am at spinning it, it may or may not spin really well, but it really does spin well. The center of this does have a brass machined tip, and then the rest of it is stainless steel. And that stainless steel is a 316L, and it was glass blasted, which means that it's just a little brighter than it came off of the printer. And the process that creates something like this, it's a fiber laser that is laser sintering layer by layer a pattern to create a solid object. So for instance, this was sitting this way in the machine, and there was a powder bed, which means there was just like a cube of powder and one thin layer on the top, and the laser came down and melted the powder into the very, very beginning of this stacked object. So if you were to slice this, then the very little prongs on the end here, those little tiny prongs were the first parts that were printed. And then after that, it continued to add more material, and the whole bed lowered a little bit, add more material, laser center another layer, it melted it to the previous layer, and so on and so forth, until eventually this gets pushed all the way down into the machine. Then we clean all of the powder out of the machine and recover the object that we've printed. And in fact, this actually is printed to a base, so we have to use a bandsaw or a wire EDM to remove it from the base plate And from there, we remove some of the supports that are remaining, clean it up, and then it's finished. And that is not the simplest process in the world, but it's a very different way of manufacturing. And I'll tell you, the reason we went down this road was because this is something that cannot be machined. This is so complex that there's no way to machine it. And if we have cavities that are unreachable by tools, it can't be machined. Also, it can't be cast. There are some areas in some of these parts that essentially are closed off from others, and it can't even be cast. So, the laser sintering, which is metal 3D printing, is the process that can create something like this and do it very accurately. So that is the spinning top. Now, to say a little more about this spinning top, it was a Kickstarter campaign a couple of years ago. So you can see I've been doing laser sintering for quite a while. And the reason that I made the spinning top in the first place was because essentially I wanted to challenge myself in learning this new software to be able to create something that was impossible with CNC machining or other techniques. So that's where we're starting, is the laser sintered spinning top. I'm showing you that simply because that was the beginning of my journey in metal printing. There's some other things that I did. This wrench was laser sintered, again, out of stainless steel. And this is the wrench for our 5mm modular mouthpiece. So there are little flats on our back bores, and this slides into the flats, and you can unscrew the back bore with that. So I made various versions of this wrench over the years. This one is laser sintered out of aluminum, and you can see it's solid, whereas this one is stainless steel, and it is hollow. So essentially I made it thinner and stronger than the aluminum version by putting a hexagon pattern inside it. And that didn't require any crazy types of software, so that was relatively simple, but it did improve it quite a bit. And then I also made these out of nylon and even machined them out of brass. We had some stamped out of steel at one point. We tried many different methods of making a wrench, which is, again, one of the simplest objects we could make. It's not even a trumpet part. If you were a machinist, then this would be something that's fairly simple to make, as opposed to most of the trumpet components are really an expert, highly advanced level of machining. This is the kind of thing that you could make in machine shop if you had the right tools. So that's where we started, with spinning tops, and then of course the wrenches. We got a lot of inspiration from different manufacturers. This is a bottle opener that was designed with generative software. So essentially it created what it thought was the best use of material in the design. And this one is made out of aluminum. And a lot of the manufacturers were very encouraging, helping me understand how we can go down this road, hoping to sell me a machine, because that's their ultimate goal. And one of them is EOS. And EOS, they really are the founders and kind of the inventors of laser sintering metal 3D printing technology. And they printed this, which is insanely cool. It is literally a leaf, or I'm sorry, a feather, not a leaf. I suppose it could be a leaf, but I've always thought of it as a feather. And you can see that it is so finely printed that the actual features are less than a human hair. I think they're down to 1/1000th of an inch. Now, I have not found anyone that has one of the EOS machines that will print me something this fine. I believe that there are too many things that can go wrong. They probably had to fine tune it to this specific design. But our goal would be to eventually print something this fine, maybe when we have a machine of that caliber. So that is an extremely impressive part. And this one is made out of titanium. The next part I'm going to show you is something that we created simply for fun. And as you can see, it's an unusual object again. This is called the twisted egg. And the twisted egg is simply a nylon and a metal piece that fit together. And you can see they have a helix to them. They are designed in such a way that it makes it look like they should not fit together. And of course they do. And I have many other twisted objects that we will release over time. This is really more of a fun toy. And there's actually a base for it. You can set it on the base. You can even spin it on the base. And it's really, its main purpose is just to get high-end 3D printed objects in your hands so you can have something to really understand what kind of durability and feature size and also quality you're going to get in a 3D printed part using a high-end machine. And like the spinning top, these two items are really things that I've offered simply to get the 3D printing and laser sintering technology in your hands so you can feel it and touch it and understand what it is. Maybe before you buy a horn, or maybe you're not interested in trumpets, maybe you just want to see that technology. These are things that we introduce simply to give you guys that opportunity. So that is the Twisted Egg. Now, those of you who have really followed my progress on laser sintering and metal 3D printing and all the other machining things that I've done over the years, most of you have probably seen this mouthpiece before, and that's my personal trumpet mouthpiece. This is not printed, it's not cast, and it's not even machined. This was made by hand, and you can see there's the nut that does come off, so I could take the nut off if I want. This is still one of our modular mouthpieces, so I can take the rim, the cup, the throat, the back bore, all those pieces, I can take them all apart. As you can see, this body was actually machined, but the outside was all hand carved, which means I had to do all that with my two hands. And that did take a long time. I would guess that probably took me 4 or 5 hours. And that is what I can create just using my own creativity and my own hands. And to be truthful about this, I probably made 4 examples of this before I got it right, which means I had 4 examples that were not perfect. So it really took me about 2 days to make this mouthpiece because I had 4 other ones that did not work. And a few of you may own those because I think 1 or 2 actually, even though they had holes and defects, I did sell them, and some of you actually own those. And I think 1 or 2 of you have even ordered these because I did offer it a couple times and I had to make more. But really, you're looking at, you know, a couple of days of work to come out with this one perfect mouthpiece. And the reason I'm showing you that is because that is kind of my baseline. If I want to create something really creative, really beautiful with my hands, how much time does it take and how much would it cost? And honestly, to make something like this, if I were starting from scratch with the whole process, 2 days of my time is really worth $2,000 to $3,000. So that's too expensive. Nobody's going to buy a mouthpiece with a special body for $2,000 or $3,000, at least not today. So I've been looking for solutions to really take my ideas and make them better and make them in a way that can be replicated more quickly and more easily. Not to mass produce tens of thousands of them, but to be able to offer, say, 100 of these to people who really want them at a much lower price point. And that eventually led to me doing a lot of different things. And eventually it did come down to actually laser sintering again. So if you look at this part, this is the mouthpiece body. And again, the mouthpiece body is the part that holds all the other components together. The rim, cup, and throat come in from this side, and the back bore and the nut come in here. And this looks nothing like one of our mouthpiece bodies, but underneath the skin, this is what the whole laser sintered component looks like. Now, that one's in aluminum, this one's in titanium. And in titanium, we can do a higher resolution. So you can see that looks much nicer and cleaner compared to the aluminum. The surface finish is nicer. Essentially, this took a lot longer to print, and it cost a lot more than that. Partially because it's titanium, and also because it was a higher resolution process. Neither one of these are usable yet. I'd have to then put an insert in there. So you can see this one does have an insert where I have machined a brass body that goes inside it. That brass body was very lightweight and very inefficient. And the idea there is that by adding this sleeve to the brass body, I can now increase the efficiency with these structural designs. And we have special software that can simulate how much energy savings we get by doing this process. So essentially, this is a conglomerate of a few different pieces. It's brass for the core, which was machined on a twin spindle lathe. And then it's got the titanium body that was press fit and with an adhesive glued onto there permanently. And then it also has this nylon sleeve that slipped over that and was glued on top. And the nylon weighs almost nothing. It's simply there to cover up all of the design. And here's one without the nylon. So the idea really was to make a very lightweight version of something like this mouthpiece while maintaining or even improving the efficiency. And this one is more efficient than that one. That was our goal. And that is really what led us to creating the entire series of Spectratron mouthpieces with the new laser-centered bodies. Here are a couple mouthpieces that are complete and using that technology. And here's one more. This one is out of stainless steel, and I flame colored it, which means I got it really hot and changed the color. And that one also was complete. So you can see all of these were my attempts to create something really cool, like really visually interesting and beautiful, while reducing the weight and also doing it in a way that I don't have to reproduce, spending 4, 6, 8 hours making one. So I can print these in a lot less time and bring the cost down. So we've talked about mouthpieces, we've talked about laser sintering and 3D printing. Of course, we've talked about experimental things like spinning tops and wrenches, and there are dozens and dozens of other things that I've made that I'm not going to show you today, and that we have had printed for us or laser sintered, or we've CNC machined. And I have boxes and boxes of things that I don't have room to display that were CNC machines, which was the process we used for the third generation Summit. And that really was a process where we take a whole chunk of metal and machine it down to one single piece, and then take that piece and incorporate it into the design of the trumpet. The advantage to CNC machining is that it's less expensive than laser sintering, 3D printing, and all those kinds of things, and even casting. That's one of the advantages. One of the disadvantages is that there's a huge amount of cost for all the tooling and all the machinery. So where I'm standing right now used to be a CNC machine, and right next to me used to be another very large CNC machine, and there were 2 more in this shop. So this shop had 4 CNC machines in it to build trumpets, and you know, the cost of all those machines and all the tooling was like $1 million or more. And there's nothing wrong with that process. The thing is, it's a very precise process. And what I mean by that is, if you do any little thing slightly wrong, it'll fail, right? And actually, laser sintering is similar to that, but a little more foolproof today, because there's automation in the software, and once you get it set up, you can kind of say, let's start, and it will go on its own, and usually it works. CNC machining, there were more factors than that, and the more material I wanted to remove from a brace like this one, the more challenging it became. So my goal has always been to make the instruments as lightweight and as efficient as possible, while giving you all the performance options in terms of varying the flexibility and the slotting and the impedance ratios and the airflow and the tone color and the projection pattern, all the things that we're known for. When you come to us to have a horn built, you know that we're going to set you up with exactly what you need. Those things are very, very important, and they're critical components to the entire process. But to reduce the weight and to do that again and again and again, precisely from 15 years ago to today, and make the exact same part precisely, can be challenging if the part becomes lightweight. the lighter it is, the thinner it is, the more difficult it is to machine. And I'll show you, this part is one of our CNC machine braces. This is a Summit brace. This is probably machined maybe 2 years ago. And that's what they look like all the way up until when we sold the machines. And this component really didn't change in design very much over the years in terms of the standard Summit bracing. It always kind of looked like this. However, the programming and the tools that we used, we constantly innovated, and the process to make it changed again and again to make it better and to make it faster and more efficient and more accurate. So behind the scenes, even though this brace always looked the same for many years, we were constantly improving the process until we really reached a limit where we couldn't make it much better. And then we took this part and we said, well, how can we make that part even better than that? Well, we found ways years ago to remove more of the material so that we could have less weight and more efficiency. So this is 2 of the top braces for the Summit 1 series. And they are held together in one piece of brass. There's a thin layer that's holding them together. I can actually break them apart if I want to. But this is a set that I am using for the 99th Summit 1 trumpet. That was a limited edition of 100. And all of these holes were custom designed to essentially make the instrument lighter, but also stronger than it was before. And if you don't know this already, by adding circles and arches and holes to some components in engineering, we can actually make something stiffer or stronger or even more flexible. So these braces resist the energy that the sound wave antinodes create movement in the tubing. They resist that better than a solid piece. And what I mean by that is they're more efficient by weight ratio. So this is a better design than this. But as you can imagine, the one with all the holes takes a lot longer to make. And a lot of these holes are very tiny. So we had to modify our milling machine with an 80,000 RPM spindle to make the little holes quick enough. Because if we didn't modify it, it would take so long that we couldn't really afford to make them at a price point people would pay. So a whole nother set of challenges. Like I said, every time we improve the process and try to make the horn lighter or more efficient, then we are always working up against the laws of physics and really the laws of just production. You know, we can either make it faster and cheaper, or we can make it slower and more expensive. But the piece that really changes there is how much it weighs and the quality. If we have high quality and a very lightweight design, it's going to cost a lot more and take a lot more time. And with the CNC machining process, this took, you know, much longer than this, you know, probably 10 or more than 10 times longer than this. So that's where we went. That's what we did with it. And we took it as far as we could. We also made a lot of different variations of braces. And here's one that gets a wooden inlay in it. So this one was CNC machined with that 80,000 RPM spindle, using a very, very fine end mill to get all these little patterns in here. And essentially what I did is I took a Celtic knot design, and I studied Celtic knots to understand how to design this. And then I drew out a Celtic knot design where it just interlocked once. So this is 2 complete pieces of rope, and they don't ever break. They just wrap under and over each other. And I have a way of making a wood reverse of this, and I can fit the wood inlay in there, and then it becomes a very contrasting bracing system. It's very beautiful when it's done, and that's an example of something we can do. You can see this one was made January 15th of 2015. So 10 years ago, this is where I was. And I'm happy to say 10 years later, we've come a long ways. Even though this is really cool, what we're doing now blows this out of the water. This one was made longer than 10 years ago. This was actually the first CNC brace that I ever made on a CNC milling machine. And I'll show that a little closer here. This was the original Nouveau design, and that Nouveau design was one piece. It took 80 hours to machine this one piece on my first CNC machine. Now, over the years, I got better machines and I got better at machining, and I probably could have machined this in 2 hours, with the newest machine that we had most recently, maybe 2.5, way better than 80 hours. But this was actually made so long ago that I don't even remember when it was. It was probably made about 20 years ago. And when I was designing this and making it and talking to manufacturers, pretty much all manufacturers told me I shouldn't be making stuff like this. It's not really possible. I would need an aerospace grade machine, and there was no real software that could do this properly at the time. But we found ways of doing it, and it did work out. But that is the original Nouveau bracing. And as you can see, this video is very, very thorough. I'm really talking about every little piece of the production process so that you understand how and why we're arriving at the 4th generation Summit. And the Nouveau trumpet was before the Summit trumpet even existed. So we've gone back a long ways already. Other parts that we CNC machine in other models are the braces for the Muse trumpet. And the Muse trumpet gets these braces, which was really pushing our limits in CNC manufacturing. The first time we ever modeled an entire trumpet in CAD software and had the entire trumpet, every little component modeled and started CNC machining was before we ever built that first Nouveau. So it's probably around, I'm guessing 2003. So what? That's 22 years ago that we were modeling the entire trumpet. As you can see, that took us all the way to the modular trumpets, which are the highest efficiency trumpets we build today. These are the Muse trumpets. And this is the bell brace. This one is the lead pipe brace. The bell brace has been hand finished. It was hand sanded. And the lead pipe brace has not been sanded or modified in any way. This is straight off of the machine. So it still has the base plate on it that was holding it in the vise. So it rotated different directions on a 5-axis fixture. And we could hit it from different directions with the end mills, and you can see it's got kind of a cool texture pattern to it because it is still a raw part. It has not been completely finished. This is how far we could push CNC machining, and what I mean by that is the machine really couldn't remove much more material than this, because if it did, it got so thin that there would be too much chatter. It'd move around too much, because we get harmonics in the CNC machining process exactly the same way we get them when we play the instrument. So it's really interesting to note that all my studies in antinodes and nodal points and the excessive vibration interference that basically disrupts the sound of a trumpet directly correlates to machining the parts that we make. So the more material we remove, the more likely we're going to have nodes and antinodes in the material and in the end mill, and sometimes even in the machine, but mostly right at the cutter tip, that could create some kind of a harmonic frequency where the end mill is spinning at a certain frequency and this material is very thin. It can start to resonate, and as it moves, it creates patterns in the metal that are defects. And when that happens, we have to throw that part out. The thinner we machine something, the more likely that's going to happen. And the best way to prevent that is to use a smaller end mill that creates less energy in the material to prevent having so many harmonics or so much energy in them. And that smaller end mill has to spin then at a higher rate. So in other words, if I were to cut this with a 10,000 RPM end mill, I could probably go down to maybe a 1/4 of an inch or even an 1/8 of an inch, although I'm not getting the most efficiency out of that 1/8 inch end mill. And at that point, that end mill could start to set this into vibration. Our machine that we used to make this actually went up to 80,000. So if I bumped that 1/8 inch end mill up to 20 or 30,000 RPM, then it could create those frequencies. There'd be enough energy to cause catastrophic failure, really. And all of our bell braces have a little tiny failure point right here, which you may or may not ever see on a Muse trumpet. See, there's a little divot there. And it's not catastrophic, but it is a defect. It's one that I could not get out of the program. So no matter how hard I tried to improve the process, that one little spot is evidence of the exact problem I'm describing. I tried to make this brace thinner and lighter than it is. It's actually fairly lightweight. And this one's a little heavier, but when this base part is removed, they're both fairly lightweight. We believe we could make these probably half the weight using other techniques, and that's the goal. But this is the limit. This is as far as we could really push CNC machining. And I'll show you some fingerings here in a few minutes where we also pushed it very to the edge of what is possible. The advantage to using that process was simply that it didn't cost a lot to run the machines once you got them all set up. The disadvantage was it did take a long time. So to make a pair of Muse braces took a very long time. In fact, the machining wasn't so long. It'd probably take, I should look up my notes, but I think it took around 3 to 4 hours to machine a pair of braces for the Muse. But the cleanup time, because there was a minimal amount of chatter and blend lines, the cleanup time is more than that. So we're looking at, to make a finished pair of these braces was, a couple days. And that just adds up to too much time, too much labor. And as you can imagine, labor is not inexpensive, especially in 2015. So that really did raise the price of the Muse. We've been trying very hard to, cap that or even bring the price of the Muse Trumpet down over time. And the technologies that are being introduced in the G4 series look very promising. We have not applied it to the bracing on the Muse yet, but we do believe that it will bring the pricing down in some materials from where it is today. And I should note that we only made 100 sets of braces in the brass variation, and that is known as the Muse MMXX, which is the 2020 model. And we will finish off making the rest of those this year. And after that, we will have a new Muse. So we'll have the second generation Muse. Other braces I want to show you are not CNC machined. And I need to back up just for a second. Before I ever CNC machine these, can you guess how I used to make them before I had machinery? I actually took a sheet of brass and I would trace out the exact design that I wanted, and then I would hand cut and hand file every single brace. So the Summit series and most of the Bravura series were actually hand cut. Some of the Summit and almost all the Bravuras were hand cut braces, and the ones that were before that were all hand cut for sure. And essentially I took a scribe and I scribed out the metal, and I took, in the very beginning, I take saws and saw out all the different areas, and then take files and file them. And I got very, very good at metalworking just using my hands. So that's how they were made originally. Now, where we're going is so very different. I'm going to show you the first braces that I ever 3D printed that could be usable. That would be this brace right here, which is 3D printed out of an extremely light material. It's so light that it could almost float in the air. This is nylon, and this is stained black. It can actually work as a trumpet brace. We can use an adhesive to put it all together. So we could make the bracing out of nylon, and you are going to see a trumpet launch later this year. It'll be the Bravura. It'll be the lightest weight trumpet we've ever built, and a step up in efficiency from really any trumpet you're going to find out there that was made in a factory. It will be the new Bravura trumpet. It won't use this exact brace, but it will use nylon as the material for quite a few of the components. And nylon proved to be very, very valuable for us. And if you've seen our pocket valves, they are printed out of nylon. And again, the mouthpiece bodies that we talked about before, they have the nylon sleeve. So this section here is all nylon in between that stainless steel. So that is the nylon Summit brace, which was a prototype. It was never introduced. I didn't sell any prototypes with this. If you find one, I didn't make it because there are none in existence. I moved on from there and I started printing them out of stainless steel. So you can see these are the same brace, but they were printed out of two different materials. So there's stainless steel right next to nylon. And the stainless steel is extremely strong. I mean, it is so strong I could stomp on this and not break it. The stainless steel is on several prototypes that we've made. You'll find some trumpets out there that were sold in 2024 that say the G4 prototype, or they might just say Summit prototype, or they might say stainless steel prototype, because I was doing a lot of different things. And there are stainless steel examples that people are playing today. And I don't know how many there are, probably maybe 5 or 6 that have this brace on it. And I've got a pair of those to show you. That's what they look like when they're around the valve set. And they are hollow except for this flat section on the bottom. The issue with stainless steel is that in order to solder this to a brass valve casing, you need to silver solder it, which is called hard soldering. And hard soldering, well, ironically, is hard, right? So we call it hard soldering because the solder is actually a harder material. It's mostly silver or some other materials that use silver, typically, and they use less lead or no lead. The one that we uses no lead, and less tin, less other materials. So hard soldering to brass with these braces is quite difficult. It's so difficult that I looked for another solution because it wasn't going to last. It wasn't going to be a solution for us. I'll show you another set. These are the H series braces that again were in stainless steel. This is 316, and there are some horns out there that were made with these braces. And essentially, I could say I abandoned that process because the soldering was too difficult, and the cleanup after they were soldered was also very difficult. So we moved on from there, but I want to show you some other components that we did make using the stainless steel laser sintering. These are the braces that fit between the third slide and the first slide. The third slide is where we put the water key, so there's a tapped hole in the middle of this one, and this would just fit between the two tubes. And the same with this one, that hex version, the exact same thing. And this is a small version of these two braces here, which are for the first slide, and that's essentially to keep that first slide parallel to the bell. So these were stainless steel, and there are quite a few horns that do have these braces in stainless. Soldering the smaller braces was much easier, so very doable. However, we did abandon that process as well because we need something that's easier. We want it to be cleaner and faster and just a better process. And I'll say this, the 4th generation Summit development is not done. It's actually, we're right at the beginning of it. I've been developing it for almost 2 years now, but the last year, all of 2024, was really focused on making the G4 series a reality, and the reality is here. It is launching right now. So if you're interested in one of the first horns, then you'll want to contact me because you know, they do exist. We are making them right now, and I'll show you exactly what they look like again more up close in a minute. But essentially, we abandoned all those stainless steel parts in the G4 series, but we didn't abandon them entirely. I actually found a way to use all the stainless steel bracing and tuning slides and other components in the Summit series, and that's going to become the 5th generation. So right now we're talking about generation 4, but I've been developing generations 4 and 5 simultaneously because of this problem. Originally, I thought the 4th generation would be stainless steel. It turns out we're not going to do that, and it's going to be the 5th generation. And what you saw on the stainless steel parts isn't what the 5th generation looks like. In fact, the 5th generation is almost completely solderless. So you'll see that several months from now. That will be something that is released in 2025. Keep in mind, the 5th generation is much more expensive than the 4th. And that's why we're developing and finishing the 4th. And like I said, the 4th generation is still being developed. So let me show you the bracing on the 4th generation as it stands right now. This is the simple strut bracing, and these braces are made out of lead-free brass. I have the marked bell and lead pipe because each side is actually slightly different. And I call them simple strut because I took the design you just saw in stainless steel and I put some struts in between. So right here, here, and here. And that stabilized the design and made it more suitable for the process we're using now, which is a high-end investment casting. So these are investment cast, and that is a whole nother process that is, it's been a lot for us to learn and to explore. And these braces, while they do look like the finished braces, they actually will be improved from this design. You may not see much difference in a month or two from now, but they are actually undergoing a slight revision that makes them even better. And this is what you're going to see if you order the strut version of the Summit. And the one that's hanging up on the wall there is the strut. I'll show you those horns up close in a few minutes. This is where we started with casting. And I'll tell you a quick story about casting and why casting has not been a good fit for us in the past and is now. So many years ago, before I ever machined anything, Jen and I sat down. Jen is my business partner at Harrelson. If you haven't met her, you should meet her. She's been with me for 20 some years in this business, and we've worked really hard to build this business. And Jen and I sat down one day and we said, you know, how can we make the process of producing the parts faster and easier? And back then I was taking the actual finger rings and the braces like I showed you, and I was hand cutting and hand filing every single piece. So to make this finger ring, I would have to have a sheet of brass, drill a hole in the middle, and carve around the outside with either a handsaw or something until eventually I got a bandsaw, which doesn't solve the problem, it just makes it a little faster. And I would hand file the whole thing until I had a perfect finger ring. And if you own one of my early trumpets, you've seen not all the finger rings look exactly the same. That's because they were all made with my two hands. Now, I was making these finger rings and I was limited to how many trumpets I could make. So people would ask me to build more and more trumpets. They'd say, oh, I want one in B flat and I want one in C. My friend wants one. And I was getting more orders than my hands and my body could make. So I thought, what if we were to cast these parts? And essentially the short version of that story is we saved a lot of money, like $14,000, $15,000. And we took all that money, that was a lot for us back then, and we took all of that and we invested it into a company that was going to cast the finger rings for us. Now, it was a huge risk, and I pushed this idea really hard, and Jen was very much against it because she thought, you know, this is more money than we've ever spent on anything. She thought it was a bad idea. And even though I listened, my hands were tired, my body was tired from doing this. I really wanted to try it. Unfortunately, the company that was casting our parts went bankrupt and we lost all of our money. And that almost broke the company years ago. We're talking like 20 years ago. However, it didn't. I just kept going, and we kept working at it. And we crossed casting off our list of options. Now, we knew that if we had an investment casting machine, we might be able to pull something like this off. But this was at a time when you could not 3D print the wax. So essentially, you'd have to have a mold to make wax forms in the shape that you wanted, and then take the wax forms, clean them up, put sprues on them, put them in the investment casting process. If you guys know this, you already understand what I'm talking about. If you don't, I'll just say this. It's a lot of work. It's a whole nother ball of wax, as they say, right? Like, it's a whole nother just process that requires a ton of effort, because once you have the cast part in your hand, you still have to do all kinds of work to make it clean and perfect. And at what point does that even make sense? So we went to CNC machining since we lost everything in casting. And essentially, we did not explore casting again until last year. And the reason I started exploring casting again was because I have a couple 3D printers that can print in wax. And Some of you didn't realize this video was going to be so in-depth, but I'm really covering everything because the G4 series culminates every single thing I've learned that is applicable to this new series of trumpets. The only thing that we're not really going to explore is the G5, which is, I've already talked about, but it's just a little more of the same thing. So going back to casting and 3D printing, I have 2 or 3 printers that can print in wax. Now, that's something that's relatively new. It's not the kind of thing where, 10 years ago, people were pushing the button and printing wax affordably. The people that were doing it in the jewelry industry, and most of them were bigger jewelry companies, like the ones that make your class rings. So essentially, to be able to cast, metal out of wax, you need to make the wax model absolutely perfect, exactly the way you want the finished product. And then you melt the wax out of an investment. So essentially, you take the wax, you put some sprues on it. It looks like a little tree when you're done because you're trying to make as many items as you can at once. And they're all hooked on these little branches. And then you put it in a slurry of essentially like a ceramic type material. After you've dipped it in enough slurries to make it thick enough, you put it in an oven and you melt out all the wax. And now you just have a hollow cavity. And it takes many hours to do this right. Then you heat up the crucible that you create out of that, and you put it in an investment casting machine, which typically is a vacuum machine, although there are spin cast versions too, but the vacuum ones are, I believe, the highest end version of it. Once you put it in that vacuum system and you turn the vacuum on and you pour the molten metal in, it sucks it through all that investment into all of the cavities that you've created where the wax was. And that's why they call it investment casting, because you're creating this investment, which is that slurry I told you about, melting the wax out, filling it with brass. The issue with that, besides the fact that it takes so long, is that you used to have to make each wax pattern individually with a mold. And because they eventually created resin printers that could do wax, that could actually print wax, then we got to the point where we could be printing these small wax forms. But the machines that printed them typically were 2 to 4 inches in size. They really weren't set up to print bigger parts, and they weren't designed for bigger machines, because investment casting can be used for all kinds of things. You could literally investment cast a giant machine part that's 6 feet in diameter, right? And the companies that do that aren't the ones that are doing the really fine details. They're completely different worlds using the same techniques. I say all of this because it's really, really pertinent to this conversation and in finding a way to do this for us, because our parts fall somewhere between giant and tiny. And there aren't many companies that specialize in doing that, and there aren't many machines designed to do it either. So going down the investment casting road has been a major pain in the butt, but also very rewarding. And it's the reason that we can release the G4 series in the first place, is because we did go down that road. So all of that to say that we figured out how to investment cast the braces and the finger rings. And we thought, well, what if we could do more than that? So we want to push it as far as we can. But let me show you the braces that are investment cast. I showed you the simple strut. Let's go to some of these others. Here is the Honeycomb. And the Honeycomb looks just like a honeycomb, as you'd expect. It is not heavy. In fact, compared to the simple strut, it doesn't weigh very much more. It's very, very efficient. These were designed to have more than twice the surface area contact, which means they're going to be more efficient. And between these two, they weigh less. So the CNC machine part is still heavier than the one that is much more efficient and also features the Honeycomb. Now, that Honeycomb isn't just for show. It's actually there because it, like the Summit 1 braces that I showed you before, these ones here, it actually strengthens and stiffens the design. So essentially, we have less antinodal energy transfer when we have this kind of a design over a solid piece. And I'm really excited to be able to use these in a trumpet. And one of the 2 trumpets we're releasing right now is the Honeycomb version. I have it sitting right here. I'll show you again. That design is more efficient than the strut version. So we've got the simple strut and we've got the Honeycomb. I'll put them next to each other so you can see both. That's what they look like. You know, the only reason you'd want to choose the Honeycomb is if you want that slight advantage in efficiency, or you just like the look of it. It doesn't cost much more in terms of the final cost, but it does cost us more to make it. And the downside to casting that I was getting to is, one, the process is a whole series of process. In other words, like CNC machining is difficult because there's so many pieces of the process and so many variables. Casting is actually exactly the same set of problems. Even though they're slightly different in terms of how they work, you have about the same number of problems and the same type of issues in the final finishing. So I wouldn't say this is any easier. It's just more efficient and lighter. And it actually costs more to investment cast than to CNC machine, but the advantage is we wouldn't be able to CNC machine something like this because it would take too long and then it would drive up the cost. So all that to say, we're trying to find that balance of what's best, and the casting technique is what we're using for the 4th generation Summit. It is fantastic. Like in terms of the results of this on the actual trumpets, what I'm going to show you and what you're going to hear, it just is blowing my mind. And the people that have had the chance to come in and play these prototypes over the last couple months, you know, the feedback I've gotten is just amazing. So that's where we are. I want to show you some of the other materials. So I just showed you brass. I'm going to show you brass and bronze right next to each other. So I'm sure you'll be able to tell them apart just by the color. But there's brass and bronze. Now bronze just has more copper content or less tin, but they look very similar. And the bronze, there are some people in the trumpet industry saying that bronze is so much better for resonance reasons, or maybe they're saying other reasons. I've spent the last 30 some years of my life pursuing brass acoustics, and I was trained by scientists who do this for a living as well from Yamaha, and I went to school for this. I did my independent studies on trumpet design and brass acoustics. All that to say, I have not found any huge advantage to bronze, or specifically the one I hear about it again and again is phosphor bronze. There's no huge advantage in resonance or efficiency over brass. And the reason there isn't is because the actual chemical content, the metals that are involved, are actually very similar. They're not very different from each other in the first place. The only place you may hear a difference is if you had the exact same bell that was spun out of the two different materials and it was work hardened the same, or in other words, it's the same hardness after it's been spun and polished, and it's the same thickness and the same taper. You might hear a slight difference. Most people actually can't hear the difference. And I say most people, I mean most professional players can't hear the difference between the two unless you change some other parameters. Now, one thing you can do with bronze, excuse me, is you can harden it more than brass. You can make it thinner or thicker, and then selling bronze or phosphor bronze maybe can be a little more truthful in terms of that one's better than this one or sounds different. But that's purely because you changed other things, not necessarily because it was bronze. So you could have made two bells where one is thicker or thinner or a different taper, and then out of the same material, they will sound different. Okay, so I just don't want you to be deceived by thinking that the material itself makes a big difference. And for instance, in our own line of instruments, we can make bells out of lots of different things. We can use a yellow brass, we can use a red brass, we could use copper, we could use bronze, we can even mix them. We can take the last 4 or 5 inches of the bell flare and make it out of copper and the rest out of brass, yellow brass or something, or whatever materials we want, right? And we've done a lot of this over the years. We can do that. In our bell selection, we have the 1, which is the number 1 bell, which is 1 insinuates or infers that it's going to be a yellow brass. It could be called 1Y. Years ago, I actually called it 1Y. And people would say, why do you have the Y on there? I'm like, well, it's because it's yellow brass. Eventually we dropped the Y, but we do have a 1G. Now the 1G is a gold brass. And what that means is that it has a little more copper content than the brass content. So if you play a 1 and a 1G, most people can't tell the difference. But the thing is, we can make that 1G slightly harder, and then it will actually accentuate some of the overtones more. And even though they could be the same thickness, slightly different material, one's a little softer and the other was a little harder, now they start to sound a little different. We can also make a 1LT, which is a thin yellow brass bell, a 1GLT, which is a thin gold brass bell. We could make a 1R, which would be a number 1 with the red brass bell. However, we don't make a 1R. And a lot of people say, why don't you have a 1R? Well, because we have a 3R. So we went to the next biggest taper in bell size, and that's the number 3. And then we allowed that one to be an R. So we don't have a 3 yellow or a 3G, we just have a 3R. And part of the reason I did that is because I don't want to have to make 45 different types of bells. We're really trying to solve problems with them. You don't need 45 bells. You guys, I think, probably need, most of you, only 3. But we offer about 20. And 20 is better than 45 when it comes to being a manufacturer. Now, 20 is still more than everybody else. I don't know of anybody who makes 20 bell variations. But we offer 20 bell variations before we start to hand hammer them and do other things. With that said, you can see why I would choose the R, the red brass, for a bigger taper, because most people that want a bigger taper are looking for a bigger, warmer sound, and red brass actually creates a bigger, warmer sound. So I'm saying all of that simply to say that when you choose your actual material for your trumpet, if you're ordering a Summit G4, you may or may not want brass or bronze. I'm telling you, there's no huge difference between them. You purely should just choose the one that you like better based on how it looks, and that's it. Because I'm not going to tell you that they sound or play much better or different. I think that's misleading, it's unfair, and I think that is dishonest advertising, and that's not what I want to do. Now, with that said, you saw brass and bronze. I also have copper. Now, copper is not in production, it's not available. If you want copper, I don't know how long you're going to have to wait, but that's what it looks like. And the reason is we have not figured out exactly how to cast all the parts in copper yet. Now you can see this simple strut bracing came out just fine in copper, no problem there. But when we go to do some of the other designs, then it becomes more and more challenging, and we're not sure when it will be finalized. And there's no rush, because the truth is, again, you don't really need copper. It's more for the visual. If you really like the visual of copper, go for it. But in terms of these braces, they're all so very efficient that you don't need it. And if you do choose copper, it actually adds weight as opposed to brass. So the brass version is lead-free, the bronze is lead-free, the copper is pure copper, so it's lead-free. There's no real reason to choose one over the other unless you just like the look of it. So copper is not yet available, but you did get to see it. And I'm going to show you in the bracing side of things some other cool braces that will become available over time. They're not available yet. So we've got some other special lattice structures, and this one actually looks quite simple in this form here. But this lattice structure can become much more complex as you start to stack the structure itself. Right now it's only one layer thick, so that's why it looks so simple. And so we're doing face-centered and cubic-centered braces as well. I'll show you the face-centered one. The first one was cubic-centered. So that's what they look like. And these types of braces will be available later at a later date. They may be limited edition. I honestly don't know what we're going to do with these designs yet, because, you know, like I said, the G4 series is going to constantly get updates, and we're going to be developing it throughout 2025, and maybe even past that. We may offer special limited editions for the next 20 years. I really don't know, but that's my hope and my goal, is to possibly have 1 or 2 designs that are only available for a month. Some may only be available for a year. At this very moment, I'm looking at making Simple Strut and Honeycomb available indefinitely. Those would be the two basic ones. I say basic, but super advanced actually. And then other ones maybe more limited edition. But essentially, we will have a lot of different variations that come out. In terms of the first and third braces, I'll show you some of those. This one was the original machined version. We replaced that with the hollow version, which matches our Simple Strut design. And it's very, very light compared to the original. I have somewhere the numbers, but it's like a quarter of the weight. And then on the Honeycomb variation, we have both the first and the third there. And then this one is the face-centered, but we have all the other variations as well. And that one is, it's by far the lightest one, because that face-centered design, which uses topology software, is so incredibly efficient. And yeah, it's amazing that we can cast these. It's been a huge amount of work to be able to make it happen. And I'm just so excited to be able to offer it to you guys. It's insane how we've come so far. Now, I'll just tell you this before we go any further in the video. You haven't even seen half of what I have to show you in this video. So if you need to take it in two parts, or you need to go make some popcorn, because I'm just so excited. The amount of different designs and experiments that I've done in the last few years would blow your mind. Like, there are so many new designs that there's no way I could possibly show you all of them. I'm just showing you the stuff that is the highlights and that is pertinent to this conversation. But if you want to come visit us in Denver and see more and get your hands on it and just get an idea for the design process and how we got to where we are today, you're always welcome to visit us in Denver. I'm happy to pick you up at the airport. Depending on your travel plans, I can pick you up or drop you off. Sometimes I can even do both. It just depends. Because of course I do have to be here working with customers and building horns. But I'd be happy to pick you up and bring you to the shop, give you a tour, work on trumpets, figure out what's going to work best for you. And maybe if we have time, go to lunch. I can do all of that included with your visit. I'm not going to charge you for that kind of stuff, because I really want you to come in here and see what we're doing and share that excitement. We can't mass produce these things. A lot of people ask me year after year after year, sometimes friends, sometimes family members, and a lot of times people in the industry, they say, when are you going to mass produce that stuff and then just sell the company and do whatever? That's just not me. I actually love doing this. The reason I make limited editions is because it limits me to create something new again and again and again. If I have a limited edition of 3 or 5 or 10 pieces, that means I get to use it 3 or 5 or 10 times and I'm done. It forces me to be creative, and that also makes me want to get up in the morning and come into work, and I never think of it as work. When I say I'm going to work, I never say that. I always say I'm going to the shop, which is really like saying I'm going to the candy store, because I have the coolest job in the world. I can't even believe it. And it's thanks to all of you who have believed in me, the thousands of you who have built or who have purchased the custom trumpets I built, all the people that have bought our mouthpieces. I think we're up to like around 7,000 mouthpieces we've delivered. And it's just amazing. And to think that, with Jen and Christine and the other people that have worked for over the years, but right now it's Jen and Christine, it's just the team of 3 of us. To think we do all of this in this one little shop in Denver with just 3 people, honestly, it blows my mind. Like every month or so, I'm like, what are we doing? How is this even possible? But we leverage so many techniques and so much technology, and just we have such a great process to be able to do this and to bring you guys really what I think is the most innovative trumpets that are the most efficient, the most versatile, and the easiest to play. I mean, it's just so much fun. And the fact that I got my heart repaired and now I can play trumpet again, it's 10 times more fun, because now I can actually pick them up and play them regularly and not get hurt. It's just so amazing. So if you want to come visit and see everything, I'll show you as much as you want to see. The wall behind me is massive, and there will be areas of this wall that will be displays of some of the components. In a showroom, I will have an entire section that is the innovation and progress that we've made over the years by year. and we'll get that on our website as well. But I just wanted you to know that if you need to stop and take a break, now's the time. I'll also tell you this. I filmed this video in several different videos all on the same day, but I have to stop. One of our cameras is a high-end Nikon, and it's primarily designed for still photos, but it works great for video too. The one that's the close-up one over here, it can only go 30 minutes, and there's a strange rule about how that all happens. But in the camera world, if you guys shoot video, you already know. But essentially, because it only does 30 minutes, I set my watch for 25 and I stop it every 25 minutes. And sometimes I go take breaks, but this is a whole day video for me. Like literally, I'm spending the entire day filming this video, which will become, an hour or something, which is still pretty long. So now's a good time to take a break before I jump into finger rings, and then we're going to look at the big surprise, the one that I didn't think would even happen in the G4 series. I knew it was going to happen in the G5, but it happened in the G4 too, and it's been an incredible amount of work to solve problems to make this happen, but the tuning slides, of course, are actually available in the G4, full one-piece cast tuning slides, which is, in my opinion, a feat of engineering in the first place, the fact that we could even do that. So let's move on to finger rings. Let me grab some. You saw the original finger rings that we used to make. They look like this, and those ones are CNC machined. They look identical or mostly identical to the ones I used to make by hand, but these are CNC machined finger rings. They did take a long time to produce the entire process, and the cleanup takes time. These are not simple, quick, easy parts. And to give you an example, years ago, like I said, I used to hand file them and make them, and then eventually we CNC machined them. And Steve Shires, years ago at the ITG, when he still owned Shires, he came up to me one day and he said, can we talk about finishing? Because they were having these major hurdles with finishing their parts. And I get it. Like they would have cast parts and they'd have to find a way to buff them and finish them. And he said, all my guys are just buffing all day long. That's what takes so much time. He says, our labor costs are so high because we're always trying to clean up all these castings. And I said, well, you should CNC machine the parts. It'd be better because once you create the process, you can get them off the machine almost completely perfect. And it's interesting to note that casting, when you cast a part and then you buff it, you can, as long as you make it shiny, you can buff it to the wrong shape, and the reflections of the light will make it look correct even though it might be way, way off. And as a machinist, someone who's always focused on precision, that's me, I'm always looking to design the part as it's intended to be used, and then take that part and finish it as close to that exact original design as possible, so we don't mess things up and create variables that we didn't intend, right? Because then I have to figure out what I did wrong, and if I'm not controlling every piece of the process, then there's a lot of variables that creep in. So Steve was having this problem. They were trying to figure out how to finish all the parts faster, couldn't figure out how to buff them faster. I recommended machining them. He did have two Haas machines at the time. One was a milling machine. He didn't want to go down that road because he didn't see how it would be possible to machine the finger rings. And in fact, I had several people different makers that had made ergonomic finger rings. Instead of calling me and buying them, they made them, and then they tell me afterwards, man, I spent 2 whole days making one set of finger rings. How do you do it? Because they were trying to make them by hand just the way I used to do it. And I explained to everybody, first off, I'll make your parts. I've made parts for many companies over the years, trumpet companies. I'm happy to make your parts. Just let me know what you need. And I'm always fair with the pricing. And of course, pricing it depends on how much the setup time is, the development, and how many you buy, right? It's just like from anywhere else. But I specialize in making really complex small parts. And if you need them, I'll make them for you. If you want to make them by hand, you can go through that trouble and cut yourself up. And it's rewarding too, so there's nothing wrong with that. But Steve decided he was not going to machine these parts. And, by the time that whole thing ended, I don't know if you guys know the story, but by the time it ended, there was so much labor costs from what I understood, from everything I looked at, because we looked at possibly buying Shires. when I looked at all the numbers, because they went into bankruptcy court and they were bought, right? When I looked at all the numbers, I saw that they had essentially, from what I could tell, taken out loans for labor to pay employees again and again, didn't get paid quick enough on their deliveries, and eventually just came too short, right? Which I can see happens, it could happen to any manufacturer of anything. And it was unfortunate that we had that change of ownership the way it happened. With that said, Shires is great. I love the company today, and the people that I know there have been great, and they make great instruments, just like they did before when Steve owned it. All of that to say, it is completely possible to machine the parts, the braces and all the other parts, but to set up the process and get it right requires someone who can figure that out. That was probably the hurdle that they couldn't overcome, or maybe they never tried. But at the end of the day, I always thought it takes so long to do the hand finishing on a finger ring compared to not having to do it, right? Like, you've got a finished finger ring off the milling machine. How long does it take to grind it or sand it? And we do all ours with sanding. We don't do any buffing, because buffing can be deceiving, where you can't see how much you've removed, and you remove too much. So all of that to say, I've always thought it took a long time to do the hand finishing on a finger ring. And then I eventually got some sand cast finger rings way back when I was telling you that we had the casting issue. They sent us some samples. When I got those sand cast parts, I was like, man, this is insane. I compared the cleanup time from sand casting to CNC machining, because that's the direction we went. And the sand casting was so much harder to clean up because there were pores. And that's what Steve was dealing with. And that was one of the biggest hurdles to casting as well, unless you get really high-end vacuum investment casting. And that's what we're doing. So I want to show you. These are the new finger rings for the G4. They are investment cast. I'm telling you, these are completely non-porous. There are no holes in them anywhere. Not any micro holes or anything. They're perfect. And the cleanup time is so much less that we can offer these as just a little bit of an add-on. And for as long as I have CNC machines ergonomic finger rings, I'll offer them as the base for the new G4. But once those are out, then the price will go up to cover the cost of investment casting these, because these are more expensive than CNC machining. And I think they're just really, really cool. I designed these to be similar to the old skeletonized finger rings. And then I designed a version of these that also has space for inlays. And those of you who remember the earlier days when I started building trumpets, I was actually a woodworker. I used to make custom puzzles and furniture and all kinds of things, desk plaques and frames, picture frames. And they were all like custom, designed for each client. Well, I love to do woodworking, and we're now in the YouTube studio where we're doing the woodworking, and I will be making wood inlays for all of these types of finger rings. So this is the inlaid version, which you will see as an option soon. And I'll show you the other variations that we have. Here's the face centered. So these are the ones that match these braces. That's the face centered. And as you can see, I was talking about before, there's multiple levels of the lattice structure inside here. So it becomes very dimensional inside. And because of that, more complex to cast. All right, and then I'll show you the cubic centered. Those are these ones right here. And these ones are in bronze. The other ones were in brass. So that's cubic. These weigh a little bit more. And then finally the honeycomb. And the honeycomb version is fairly lightweight, because that honeycomb in the middle, I think, is 2 or 3 millimeters thick. I don't remember what I designed there. And we will have these in several different sizes. So I will be updating the website over the next couple months as we have all of them kind of solidified, the sizes. But just like the CNC machine versions we've had in the past, we will have a size for every size fingers. Now compare that to as far as I could go with CNC machining a fingering. This is a CNC machine fingering out of brass, and I do not remember the cycle time on this, but I think it was 8 hours on a machine that really cost, you know, over $100 an hour to run. So obviously, and I made this, oh, when did I make this? I probably made this 9 or 10 years ago. And then I had one laser sintered a couple years ago out of stainless steel, and that's what it looks like. Side by side, they look pretty much identical. Now, to machine one out of stainless steel, we never did do it because we figured the cycle time would be about 36 hours or something, and it never made sense to make one. I did make a few of these in brass, but yeah, stainless steel never happened. And of course, I only did that just to see if it was possible early on when I was first laser sintering metal, and now we know it is. Now, the new finger rings are very different than that design, and I'll show you again. Obviously, I didn't put honeycombs everywhere. So we just put them really where they could be a support. And even though our finger rings do add efficiency and they do prevent the antinodes from transferring energy, they don't need to be very heavy. So especially with all the new innovations that we've had the last 10 years, it's not really necessary to make it much heavier. It's really to carry that theme through more than anything else. So again, truth in advertising there. So the big surprise on the G4 series that I really wasn't expecting, and I didn't think would be a part of the launch or the release, is going to be a huge bonus for you, for anyone who buys the new G4 Summit, simply because this is a huge upgrade that we didn't actually think was possible, and working with different manufacturers and possibly even bringing all the casting equipment, upgrading to like the really high-end stuff in-house. It looked like we probably couldn't do this one thing. And we, you know, recently in the last few months discovered that it is 100% possible. We can now cast the tuning slides for the G4 series. Now, even though the G5 is months away, I do want to show you my process getting to the G4 tuning slide, because I actually didn't think I could even attempt this. I understood it wasn't possible to do. So I was laser sintering the tuning slides from nylon, which is what you see here. And the nylon, this nylon again is, it's dyed black. So it could be other colors, but really black is the color that we have been using. And from there, we moved on to trying it in other materials. I went to stainless steel, tried that, and titanium and aluminum. This is the aluminum version. It's extremely lightweight. It's not as efficient as brass. However, it's more efficient than a standard tuning slide that you would find from another manufacturer. And it's so extremely light that the weight savings are going to be huge on the G5 series. So I just want to show you my process, get into the G4. Technically, I developed all of the G5 tuning slides before I even tried the G4 because I didn't know we'd even be able to do it. So this is the aluminum version, and I actually had this one sintered with the tuning slide water keyhole in there. And the way we deal with these is you can't solder to aluminum. So with this tuning slide, we still have the nickel inner tubes because we use nickel against brass for all of our tubes. It's more lubricous, and it's a great solution to preventing tarnish and corrosion and other things when you do brass on brass. And also, you just have better action. It's smoother. But we can still put the nickel into the aluminum. We just have to laser weld it. And we do have a laser welder, so we can do that. We've been doing laser welding for many years. And the water key, which oftentimes is the Saturn water key, that's the one we recommend. It can be laser welded directly to the tuning slide as well. I have had no issues with that. It works, and it's great. That's aluminum. This one is stainless steel. And actually, I'll compare the two. Here's the stainless. So that's 316 stainless again. And then here is the aluminum. The stainless is much heavier, much more efficient. And we have, you know, a lot of challenges when it comes to laser sintering something like this. essentially I had to use special software to create a scenario where it could be printed without having supports inside the tube. Now, when I've asked different companies to print these for me, they've all put supports inside the tubes until we figured out the secret magic formula to do it without. And the funny thing is, we know how to do it, but if we ask someone to do it, sometimes they'll say it's not possible. And then when they finally do try, because we've designed it that way, it actually works if we can get them to try. So, but we've got that all figured out now. So that's stainless steel. We also did them in titanium, and that'll be something that we introduce as well. Titanium is in a weight class between aluminum, which is super light, and stainless, which is heavy. It's much lighter than the brass version. I don't exactly know how much lighter. I would guess probably 30 to 40% lighter than brass, and much more efficient. So this is the titanium. And again, the titanium we can have printed in a much higher resolution because we're already paying a lot more to have this material in the first place, so we can up the resolution and it comes out very, very nice. So that is titanium. With these, I started experimenting with laser engraving. Now, I've been designing lots of different patterns and drawings and themes for trumpets for many years and doing laser engraving. And before I did the laser engraving, I used to just do the hand engraving for many years. What I've done now is I've taken the stainless steel and I've polished it to be a very, very fine, perfect polish, which takes quite a bit of time to go from the sintered to the polished, but that's what we can achieve. And then I started experimenting with taking this finished tuning slide and then applying a pattern to it. So I'll show you the first one that I have sitting here. This one is essentially a microchip processor board. So in other words, you can imagine that this could be representative of an actual circuit board. And I did deep engraving all the way around the tuning slide with a circuit board drawing. And it turned out really, really well. It's amazing. Like, this is extremely deep. You can feel it. I did lots of other patterns. This one is a musical pattern. There are actually keyboards and guitars and trumpets and things drawn into this, even though it's not obvious. And from there, I tried some like doodles, things like that. So this one, I actually created a texture that is just something to make it look more interesting than the original laser sintered texture. So I created a texture here, and then I actually drew a bunch of doodles, and they look like that, which turned out just really, really cool. So these are becoming one-off trumpets with the stainless steel variations. And you'll probably see some of these come up on our website in the next couple months because I will be putting them together. Eventually, these will be actual artwork that will be available for the new G5 series. So again, we're just talking about G5 tuning slides right now. Get into the G4. So that one is, again, another really cool texture I created. And I'll show you one more here. This one is a texture that I called neurons, and essentially I thought it looked like different layers of maybe your nervous system or in your brain or something. But a lot of other people have looked at it and said it may look like tree growth or roots or something else. And I want to show you one more thing. This is a stainless steel one that was not cleaned up. So when I actually do the laser engraving, they look like this before I do the final cleanup. So once they're all cleaned up, I remove all that soot and slag, and then it looks like a finished tuning slide. Now, that brings me to the G4 series. What I really wanted to achieve here was the G4. Originally, it was going to all be in stainless steel or titanium or aluminum. As I got further and further into this and started testing casting and other options, trying to have parts laser sintered in copper, having successes and failures all over the place throughout 2024, I discovered that it was possible to make the brass and the bronze and the copper variations as the G4 and take all the other materials and make them as the G5. And I explained that earlier, but I didn't know that when I started this. And this is what happens when you are trying a lot of different things. You're prototyping, you're testing different materials and different techniques, which I've been doing, for over 30 years. I've been doing this kind of stuff. But in the last year, I realized I actually had 2 different models on my hands. And when I discovered that and realized that's the direction we were going to go, it was after I had already sold our CNC milling machine. Now, our CNC milling machine used to make the tuning slides. And the idea was now to make the G4 series out of brass and bronze and copper-based metals instead of steel or titanium or aluminum. But I sold the machine and I didn't want to buy another machine or pay someone else to make the tuning slides for us because they're very expensive to make. We've had them quoted. It costs about $2,000 to $2,200 to have one of our SWE tuning slides made for us if we have another shop do it. And that's before it's been laser welded together and assembled and finished. So that's just the price for the machined component. In other words, 2 halves of this, which is the CNC machined version. So you're looking at $2,200 for a pair of these just to be able to assemble them into a tuning slide. And if we weren't making them ourselves, it would not make sense for us to offer those. So in full disclosure, explaining how all this happened, I sold the machines before I realized we could have a G4 series out of the copper-based metals. And when I discovered that, I thought, well, shoot, now we've got to solve this problem with the tuning slides and see if we can make them out of brass, bronze, and copper. And we tried and tried and tried and failed, and we couldn't figure it out. And I want to show you some of my examples of where I was getting close. So this one is the original simple strut design that is designed to work with the simple strut braces. So the braces and fingerings I showed you, this was the matching set. And I'll show you up close here. So if that makes sense, what I did is I took 4 ribs and I put them throughout the tuning slide, and we attempted to cast them into the tuning slide. And we had a lot of different types of failures, but what we discovered was if we had vent holes in the tuning slide to suck the material into the cavity, because these thin walls, the metal's coming in from the top and getting sucked all the way down here, you need more vacuum suction. We were putting these holes in to be able to suck it through, and then experimenting with filling the holes different ways. And all of that really just wasn't the best solution. What we discovered was putting a couple holes in actually is a great idea, and we can fill them. And right now these ones are filled with actual screws. Believe it or not, that actually works great. There's nothing wrong with it, as long as they're sealed perfectly and they're designed to be the right thickness. But in that process, we discovered that we probably don't have to have any holes or any screws. So at this very moment, the finished versions that we have do not have holes, and they don't have screws or anything filling the holes. But I want to show you the variations that we created and the things we discovered we could do and how we ended up with the final version, which will be available in the new series right now. And we'll talk about deliveries and timeline on that soon. But you can see there are a couple little holes here on either side, and there are actually more holes that were filled with soldered in rod. So if you look close, you can see some other spots. And that just wasn't acceptable. However, putting in these little ones with the screwed in studs actually allowed us to imagine what we could do with a modular weight system. So in other words, if we could add mass in certain places for different antinodal challenges, like say you're playing a certain partial and the antinode is landing somewhere in there and you want to increase the mass to prevent that from happening, we could have a very thin tuning slide, maybe one thinner than this, and then we could take that tuning slide, use the hole method, or even put holes in even if they weren't included, and then add mass with different type studs that are different masses that we create. So this turned into an opportunity to try new things, and that led to this, which is crazy looking. So check out that honeycomb tuning slide, and I literally put a whole bunch of screws in this one. And the idea was to fill those holes and solve that problem. But in addition to that, we can actually change the mass in very finite locations so that we can experiment with improving efficiency on certain partials. Now, we have software that helps do that, and it's not the kind of thing that we haven't done in the past. We just have never done it with screws. We've never put holes in tuning slides like that. In the past, what we've done is we've added mass in the design and machined it in there, or before we were CNC machining everything, we would make parts and then solder them on. But the idea is, if you have a piece of tubing that is very thin, especially on a bent tube that wasn't machined or cast or sintered, like a regular tube that was bent, when you do that, the outer part of the tube gets thinner. And if an antinode lands anywhere in there, in other words, you're playing a certain partial and the antinode lands in that section, it will exert enough high pressure to set the tubing into motion, and that will set into motion much easier if it's thinner because it doesn't have enough mass to resist it. And this is where the momentum spinning top comes in. The reason that I ever made those in the first place was to illustrate how Newton's laws of motion really work and how that's directly related to what happens in musical instruments. And if you want to learn more about that, you can go on the Momentum website or on the Kickstarter from years ago and see all the stuff that we did on that. But essentially, we're not offering this, we're not offering this, but these are directions we could go someday if we see a reason to do it. So there's opportunities here that we did not expect. And the other thing we didn't expect was for it to actually work, for us to be able to cast the whole tuning slide. I really, really hoped for that, but I didn't expect it to happen. Now, all the ones that I have here have holes that were filled. So I don't have any right now that don't have holes that are filled. However, we have a prototype that it does not have the holes in it. And what we discovered was with this kind of a design, essentially when we want to improve the efficiency on certain antinodes, we need to add more mass. The weakest area is always on the outside of the curve because it doesn't have any bracing inside it. We discovered that by making the thickness of the wall gradually thicker all the way to the end and then make it thin out again as we get back to where the legs are on the tuning slide, one, it solves the casting problem. It can actually pull enough material in and we can cast it. And two, it improves the efficiency even more. So the solution to all of this was to design essentially an algorithm that makes it thicker when it gets all the way to the end. And that's what the final version looks like. I want to show you some other variations of tuning slides that we will possibly offer in limited editions, or they just might be purely experimental. This is another one that would be related to the simple strut design. This one again has the 4 ribs on it. It also has what looks like rivets in the middle here. They're not, they're fully cast in there, but this is a more robust, higher efficiency version. To me, it reminds me of something from the Renaissance period, you know, like it looks medieval or something. And that may become an option someday. This is the exact same as the original simple strut. This will be an option for sure, where we have a filled in section in the middle. And that really isn't because we need a lot more efficiency. This is actually very efficient. It's simply because we have an area to be embellished or engraved, and we could laser engrave or hand engrave, or we could even put other things in there like inlays. So let's say we use those finger rings that have the inlay space. We can create an inlay space in this and then put matching inlays in there. So these are the prototypes that will be coming in the future. And then I want to show you a couple other ones that are pretty cool. Trying to think of what I did with one of them. I have one that's finished that looks like this. I'll grab it. So this one is a very simple lattice structure that's just 2-dimensional. Very effective, but also very simple. And then this one is a 3D TPMS structure. So essentially it's a 3D hollow repeating pattern that is in full 3 dimensions. It's very, very lightweight and extremely strong and effective, and it essentially makes the tuning slide much more efficient with this one. So now I think we should probably play this one. Let me grab one of my mouthpieces here. Looks like I have Spectratone Blue. There we go. Now this configuration is the Honeycomb, and it says right on here, Honeycomb Bronze. So I'll bring that up here. Honeycomb Bronze means that all of the braces and the fingerings and the tuning slide are actually in bronze. So this one features brass as most of the horn, and then bronze braces and fingerings, including the honeycomb braces down here on the first and third. So those are also bronze. You can see they're a different color. And all the specs, of course, as always, are engraved right on the valve set. And the bronze doesn't look a lot different. This is actually number 1. So this is the first G4 that we have built, the first one that is not a prototype. And like I said, the tuning slide will slightly change. The bracing will very slightly change. Not enough for this not to be number 1, just slight improvements. And the lead pipe and bell configuration on this one is number 1 for the lead pipe and 1X for the bell. And you can go through our lead pipes and bells and discover what all those mean. But this demo is kind of a middle of the road, big, warm, and also vibrant. They can really work in any playing situation, from lead work to brass quintet to orchestra, playing big and small works. And when you purchase a new Summit G4 and I build it custom for you, you get to choose your lead pipe and your bell. Now, the lead pipes that are available are a pretty diverse set of options. Number 1 is the one we recommend for most players. Number 4 is a little bit bigger and warmer. And then we have some that are smaller, so we can really build whatever you need. If you want it to be a high efficiency setup that uses less airflow, the VGR system will allow you to achieve that with the correct lead pipe. And we for sure will offer at least 3 different lead pipes for now in the G4 series. And on the bells, we are allowing that to be completely open. You can choose from any of our bells on the G4 series. So we've got a wide array of them. If you go to our website, yharrelson.com, you can see them all. While you're there, you should make sure to sign up for our email updates so you know what's happening and when new things come out, and you'll learn more about the G4 series. You should also press subscribe since you're right here on YouTube, and you can do that now to essentially be able to watch other videos on this series. There is another video coming out that is the top 10 reasons you should consider purchasing a G4 Summit. And that video is very short compared to this one. It's only like 10 or 12 minutes. And it will walk you through all the innovations in a very short amount of time. But this video really is diving deep to help you understand how and why this is so different from everything you've ever seen. That feels very, very nice. Let's play the other one. Now this is the simple strut, which is serial number 2. And it says strut red brass. So, and this one also is lead pipe 2, bell 10. So that's the bracing variation. And red brass, meaning all these cast parts, everything that we're doing in brass is red brass, meaning it has more copper content than the normal yellow brass that we use for machining and for bells and all the other components. The red brass is slightly, it's similar in color, but it's slightly more copper content than the yellow brass. So your options for having the bracing come in red brass, bronze, and eventually copper once we figure that out. So this is the red brass, and you can see it really doesn't look that different from the yellow brass, but technically it is red brass. And we'll compare the two side by side so you can see the differences. And like I said, this is a lead pipe 2 bell 10. It's going to be much bigger and much warmer. And it's very, very big. And I don't even have my tuning slide pulled out, but it feels really nice. The fingering options are just like the previous generation of Summit in terms of you can choose the size and you can choose the placement. So if you decided to go with these skeletonized ones, which are the standard contour, I think is what we call those, then, oh no, they're not the contour. These are the simple strut. So these are the simple strut finger rings. If you choose those, then you could choose them in different sizes. We have 2 sizes of the pinky hook. We have one or both sizes in the pinky rest. So you can rest your pinky on there just like the previous pinky rest hooks that we had in the past. And you can also choose from different sizes of the third ring and the thumb ring. And the same with the Hex series. If you look at these two side by side, then you can see, essentially those finger rings are the same shape. And if you look at the pinky rings, then they are essentially the same. It's just one is a hook and the other is a ring. And all those options will be available in multiple sizes. You can choose from the Saturn water keys. We may have some new actual rings for the Saturn water keys. We've been developing some new things there. But essentially they'll work the same. But for now, the Saturn water keys are standard on the Summit. They're the ones I recommend. If you want to go to a motto or some other style, those may be options, but they're not the standard. The first 20 to 30 Summit trumpets that we sell this year will have the last generation of our machined lead pipe. So this lead pipe was fully machined on the CNC lathe that's right behind the camera here in 4 segments, and it's basically precision machined to be very strong, very efficient, and very precise. And it has the VGR system built into it, so you can adjust the flexibility, the slotting, the impedance ratios to get the maximum resonance and the airflow, all by changing the insert that goes right here. And then you just screw your receiver back on and put your mouthpiece in, and you're good to go. We can make any of our Summit trumpets feel as wide open or as tight as you like, both with the lead pipe selection and with the VGR system, and of course with the modular mouthpiece. And our modular mouthpieces are available to complement the horn. We can set it up in your size, in your rim shape and diameter, and comfort level. We can do all those things to match exactly what you need to pair with the horn and create the kind of playability and flexibility and performance that you're looking for. So our mouthpieces are highly recommended. They're not actually required. You can put any mouthpiece into our VGR system on the G4 series and on the Muse system. So it's not required, but we do highly recommend it because we can customize it to fit you perfect. And when you come into the shop and you want to figure out which lead pipe and bell is best for you, the best thing we can do for you is walk you through all the options on the Muse trumpet, which is fully modular. In the Muse system, you're going to have essentially the same lead pipes and bells that you can choose from on the Summit, but we can change them in just a few seconds so you can find what works best for you. And then you'll have a one solid trumpet piece built for you that will be the configuration you want to keep. So I highly recommend coming to visit us in Denver, Colorado. It's not necessary, but it's recommended if you haven't played on Harrelson equipment or if you don't know which lead pipes and bells might be best for you. But a lot of you may be purchasing a Summit G4 because you already own the Muse, or maybe you own one or two Summits, or a Bravura, or one of the other horns that we've built over the years. And you may already know a lot about our lead pipes and bells and have a good idea of the configuration. Maybe it's not as important for you to come and visit, but it's still a lot of fun, and I'm sure you'd enjoy the visit. So this wraps up our video. This is really as much as I can share with you at this point on the Summit G4 series. And as you can see, there are the two variations that we're offering right now, side by side. The simple strut is this one, which has the lighter bracing. And of course, the Honeycomb is the one that looks just like a honeycomb with the hexagons, a little more efficient, and obviously a little bit more expensive. These are much lighter and much more efficient and more resonant than the previous generation. And I'm just really excited to be able to launch these and get them in your hands, get more feedback from you, and really just take trumpet playing to the next level. Obviously, the engineering and the production processes have improved vastly, and I welcome you to join the Harrelson family and experience it for yourself. Thank you, and I will see you in the next video.